is Lesson 11.3, page 600, Shapes of Distributions. In this lesson, you will learn how to describe the shapes of data distributions, how to use the shapes of data distributions to choose appropriate measures, and how to compare data distributions. Let's talk about describing the shapes of data distributions. A histogram is a bar graph that shows the frequency of data values in intervals of the same size. A histogram is another useful data display that shows the shape of distribution. Now, I'm pretty confident you have drawn histograms before. I always learned when I was in school that a histogram is just a bar graph with the bars all pushed together, and each bar represents an interval of data. Now, when you do a histogram, you could get three pictures. One picture would look like this. This is called skewed left. And the reason we call this skewed left is, as you notice, there's a tail on the left, and most of the data is over here on the right. This is called skewed left. Then we have a histogram that could look like this. This is symmetric, where the left side looks similar to the right side. Okay? Now, if that is the case, it's called symmetric. Now, if all the bars of a histogram are about the same height, the distribution is flat, and that would also be symmetric. So if I drew a histogram where all the bars are the same height and it's flat across the top, that would be symmetric also, according to what this is saying here. And then finally, you could get a picture like this where the data is more to the left, which means the tail is to the right. This is called skewed right. Here's a practice question. This frequency table here, and let me circle it, this frequency table here shows the number of raffle tickets sold by students in your grade. Display the data in a histogram, describe the shape of distribution. So first of all, to make the histogram, you can see what they did. They made a bar which represented 1 to 8 tickets sold. They made a bar that represented 9 to 16 tickets sold. They made a bar that represented 17 to 24 tickets sold, and so on. Now, you notice how we had 5 tickets, or 5, I should say, people sold 1 to 8 tickets. Well, that's why we have a bar drawn 5 units high. This is showing that 5 students sold 1 to 8 tickets. Now, 9 students sold anywhere from 9 to 16 tickets, which is why the next bar is 9 tall, and 16 students sold anywhere from 17 to 24 tickets. Okay? So that's why we have a bar of 16. And I think you get the idea. That's how we would draw the histogram. Okay? So we drew, and I should have said this first, I guess. We should draw and label the axis first. So you got to be careful when you draw these up. You can't just start drawing. You should check. You notice how my highest frequency is 25. I need to make sure I draw a graph that at least gets up to 25. I would let you use graph paper to help you draw these out. I always like to have some graph paper. It made it easier to draw. So again, just like when you draw a graph, you got to think about your scale before you start. We don't want to start drawing and then find out, well, geez, my graph doesn't fit. So look at your frequencies to determine what scale you're going to use, and then you can start drawing it out. Okay? Now, when we look at this data, let me just cross this out for a minute. Do you notice this data, it looks like the left side and the right side are pretty close to being the same, so this data would be symmetric right now. Okay? That would be the best way to describe it. That's symmetric. What I'd like you to do is pause the video and try this question. I want you to draw a histogram. This data shows the number of pounds of aluminum cans collected by classes for a fundraiser. Display the data in a histogram and then describe the shape. Pause the video and go ahead and do that. And I'm back, and you can see I took graph paper, and the first thing is before I drew this out, I had to determine, you know, what's the greatest frequency. It went up to 34, so I had to pick a scale. So do you notice my scale? I decided to go up 5 at a time to fit this on my paper well. So there's my scale. We're going up 5 at a time, and there are my different intervals. This is the number of pounds of aluminum. Here's the frequency, and I just started drawing my bars, okay, for each of those frequencies. Now, when I got done drawing, the next thing is, do you notice how this tail, we have a tail on the left, the data is more to the right, so this is skewed left. This data is definitely skewed left. I have a tail on the left. Most of the data is to the right. Now, when you draw a histogram, we'd have to know what measures would be best to approximate the center of the data and what would be the best measure of variation to describe the data. Okay? So, if your histogram is symmetric, it would be best to use the mean to describe the center and to use standard deviation to describe the variation. Okay? Now, when we are symmetric, like we have in this picture, the mean and median are going to be pretty close to being the same, so it's fine just to use the average. You can use the mean to describe the center of measure. However, if you have a skewed graph, it is better to use the median to describe the center. You can see in the picture here, the mean would be right down the middle, but here's the problem. Most of the data is over here. So this is skewed to the left. So the median would be a better measure of the center of the data. And the 5-number summary would be a better way to describe the variation. Remember, the 5-number summary you use when you make a box and whisker plot. You know, the 5-number summary will show you where's the middle 50% of the data based on quartile 1 and quartile 3 numbers. Let's take a look at the sample that addresses what we just talked about. A police officer measures the speeds in miles per hour of 30 motorists. The results are shown in the table to the left. So here's 30 motorists. Okay? And so we're going to make a histogram of the data using 6 intervals beginning with the 31 to 35 mile per hour speed. So here's 31 to 35 mile per hour speed, here's 36 to 40, here's 41 to 45, and so on. And you can see there was one person that drove 31 to 35 miles per hour. We had 3 that did 36 to 40. We had 5 people that were driving in the 41 to 45 mile per hour range. 46 to 50, we had 6 people. 51 to 55, we had 11. And 56 to 60 miles per hour, we had 4 more. Okay? Which measures of center and variation best represent the data? Well, let's take a look here. Do you notice how this data is definitely tail left, so this is skewed to the left. All right, so if it's skewed, the median would be the best measure of center. Okay, so I'm going to want to use the median, and we would want to use a 5-number summary to describe the variation. So I could type all this data in my calculator and make a 5-number summary, and that would give me the median, and it would give me the middle 50% of these numbers. And then finally, the speed limit is 45 miles per hour. How would you interpret these results? Well, when I'm looking at this, this is what I'd say. There's an awful lot of people speeding because I'm counting this up. There's 21 people that are traveling over the speed limit, and 5, 3, and 1, there's only 9 not. A majority of the people are speeding, according to this histogram. Okay? What I'd like you to do right now is pause the video and answer this question. This is a listing of email attachments sent by 30 employees of a company in a week. We would like you to display the data in a histogram using 6 intervals beginning with 120. Which measures of center and variation would best represent the data then and explain? So why don't you pause the video and do that. And I'm back, and here is a histogram, and I should write in here my email attachments. Okay. Now remember, before you just start drawing, you got to double check. The most I had 10 people that had attachments anywhere from 61 to 80. So I had to make sure my frequency could at least get up to 10. And there's my histogram. Now when you look at this histogram, it looks to me like it's fairly symmetric, like the left side and the right side are kind of mirrored. Okay? So if that's the case, the mean would be the best measure of center, and the standard deviation would be fine to use to measure my variance. Let's talk about comparing data distributions. Emoticons are graphic symbols that represent facial expressions. They are used to convey a person's mood in a text. This double histogram shows the distributions of emoticon messages sent by female students. So that's the top histogram. This would be female students. And then down here would be a histogram of male students sending emoticon messages. We want to compare these. So let's take a look at them carefully. First of all, when we look at the female histogram, it looks like the distribution is symmetric. And if it's symmetric, the mean and the standard deviation would best represent the center of the data and the distribution of the data for the females. However, when you look at the males, it's pretty obvious that this is definitely tail right, so it's skewed to the right. Okay? So if it's skewed, the median and the 5-number summary would best represent the male center and distribution of data. Okay? From there, let's compare the two. The mean of the female data is probably in that 30 to 39 interval. So the mean to this data is probably somewhere in here. But for the male interval, the mean is, I should say the median is probably in here, because think about it. Let's add up the males. We had 14 in the first bar, 12 here, 6 and 2. Well, if I add up 14, 12, 6, and 2, I get 28. So if it's 28, half of 28 is 14, so really the median of this data is probably about here. So for the males, it's probably actually at the bottom end of the 10 to 19 interval. It's probably, I'd say it's probably closer to 10, which would be the median of the data. So a typical female student, we said it'd be here, would be about the middle. Female students, the typical female student is definitely sending emoticons way more than a typical male student would. Okay? The female student is also, data I should say, is more variable. You notice we have females sending as little as 0 emoticons, but we also have a group of them sending as many as 59 emoticons in text messages during a week, where for the males the low number would be 0 and the high is in the upper 30s. So again, much more variance in the female emoticon messages. Let's pause the video here and have you try. I want you to compare the distributions using the shapes and appropriate measures of center and variation. This is years of experience. We're comparing the years of experience between company employees and professional football players. Go ahead and do that. And I'm back, and first of all, it looks to me like the football players, they are definitely skewed right, which means the median and the 5-number summary would be the best ways to measure center and variance data. However, the company employees, as you can see, they have a symmetric look to their histogram. So the mean and the standard deviation would be a better way of measuring these. So I kind of try to draw those in. The median of the football players would be around, I'm estimating, it's probably around the 6-year area, okay? So the center of data would be about 6 here, but for a company employee, their middle data would be about 12 years of experience. So the normal company employee is going to have double the experience of a professional football player, all right, as far as time at work. And now, the other thing would be the variance. Let's compare the variance. You notice how a pro football player could have as little as 0 years of experience. At the very top end, they'd have 20. So there's really a range of 0 to 20 here, where for a company employee, it goes from 0 up to 23. There's more variability also in the company employee data. To finish up the video, many real-life data sets have distributions that are bell-shaped and approximately symmetric about the mean. So a lot of real data would be symmetric, okay? For now, the following rules can help you see how valuable the standard deviation can be as a measure of deviation. Now, we're not going to get real deep into standard deviation. You've already learned how to calculate it on your calculator, and I've mentioned this in class before. So this is something I would get in your notes, though. About 2/3 of the data lie within one standard deviation of the mean. So when you calculate the standard deviation, 2/3 of your data will fall within that standard deviation of the mean. 95% lies within 2 standard deviations of the mean, okay? And data values that are more than 2 standard deviations from the mean are considered unusual. Those would be like your outliers, okay? For this course, we're going to focus more on this. We're going to focus more on 1 standard deviation within the mean. I think it's important that you remember that 2/3 of the data basically lie within 1 standard deviation of the mean. Let's look at comparing data distributions. This table shows the results of a survey that asks men and women how many pairs of shoes they own. So you can see they asked 35 men in the survey this question, and we had 40 women. And they gave you some details here. They did a 5-number summary of the data, and so they made a box and whisker plot of the data. Okay? So, after making the box and whisker plot, describe the shape of each distribution. Well, for the women, you can see that this is symmetric. The box and whisker plot's in the middle. We don't have the box pushed way left or right, and the whiskers look about the same length. So for the women, it is symmetric. But for the men, it's definitely skewed right because the box is pushed left. Most of the data is left. We got this long whisker on the right. For the men, it's definitely skewed right. For part B, compare the number of pairs of shoes owned by men to the number of pairs of shoes owned by women. Well, I hope it's obvious to see that as a whole, women are owning more shoes than men. In fact, the middle number of women owning shoes, they own 14 pairs. So the middle group of women are about owning 14 pairs of shoes, where men only own 7. In fact, 50% of men own anywhere from 5 to 10 shoes, where 50% of women own anywhere from 12 to 17 shoes. So it's easy to see women as a whole own more shoes than men. And then, about how many women surveyed would you expect to own between 10 and 18 pairs of shoes? Let me erase this out. Now remember, this is 50% of the data. Now here's 10 shoes owned, and here is 18 shoes owned, and this is 50% of the data. So if I throw this extra on the end, that might be like 2/3 of the data. If I take 2/3 of 40, you're going to get how many women own shoes. 2/3 of 40 is about probably around 27 women. This wouldn't be the kind of question. This question you'd have to estimate. So I would give you leeway on that. It's not something I could give an exact answer to per se. We'd have to give an estimate to it. I just want to know that you could be in the ballpark. I think I'm going to pause the video there. If you have any questions, make sure you ask in class.